Hello, everyone. I'm really excited to be here to briefly review this paper titled Observations on the Use of Statistical Methods in Food Science and Technology. And for me, before I go on to review a research article, I always like to presume the quality of the article by checking out on the ranking of the journal that published the article, and of course, the research profiles of the authors when possible. And the fact that this particular journal, has been ranked by scimag-ojr.com as, a Q1 journal in food science gives me some hope that this paper contains some good quality information. Also, looking at the research profiles and the contributions of the authors of this paper, to the field of food science and technology, I'm, much more hopeful that reviewing this paper won't be a waste of time for you and me. So, as it is the tradition, the authors of this paper, started by telling us, the vital roles statistics plays in FST research. And by FST, I mean food science and technology. As a matter of fact, statistics is important, whether you are planning an experiment, trying to analyze your experimental data, interpreting your experimental findings, or optimizing a food processing method. But according to the authors, many food researchers still misuse statistics, and I would like to quote them here. They said, experience shows that many workers frequently select the wrong test or use the correct test in wrong situations. For instance, many researchers often fail to pay attention to important concepts prior to comparing mean values. So these authors, they just try to highlight what the problem statement is. And, since the importance of proper application of statistics can't be overlooked, the authors have therefore, written this paper to achieve 3 specific objectives. The number 1 objective is to explain some concepts regarding data analysis in food science and technology. Then to provide some statistical information, and finally discuss and present some published examples of mathematical modeling. And I must tell you that the authors of this paper have actually adopted a sort of an expository approach in achieving these objectives, which is why they discussed extensively with examples some statistical concepts which we often need to apply as food researchers. And this include normality and homoscedasticity, which is also known as uniformity of variance, parametric statistics such as t-test, ANOVA, etc. And also they talked about non-parametric tests like Mann-Whitney, Friedman, etc. So, talking about normality, let's start from where they started. So according to the authors, many food researchers don't pay attention to the normality of their data. So, and by normality, we mean a data set that conforms to a normal distribution. And by normal distribution, it means that at least approximately 95% of the data lie within the range of the mean plus or minus 2 standard deviation, or you could say that about 99% of the data is within the mean plus or minus 3 standard deviation of the data. And a quick way to visually test if your data is normally distributed is to actually plot a histogram of your data. So if your data follows a bell curve shape, which is what we can notice in these 2 figures, then there is a good chance that your data is likely a normal distribution, or it's normally distributed, even though it is always good to conduct some statistical tests such as the examples cited by the authors, to really confirm that your data set is normally distributed. So, and the reason for this is that experimental data can always take different forms. When you have data, relating to chemical constituents or contaminants, these are often, conforming to normal distribution. But in most cases, microbiological data do not conform to normal distribution. It could either be log normal or binomial or Poisson distribution. So it is important to identify the statistical distribution of your data before carrying out a statistical analysis. So, but on this note, I would just like to refer us to, a few pages where you can find more information about normality and normal distribution in the paper. If you go to pages 138 to 141, you can find more information about, normality and normal distribution, in the paper. We've got limited time. This is why I have to just, skip over some things like this. So moving on, one other thing, many food researchers don't pay attention to, according to the authors, is the homoscedasticity of their data. And homoscedasticity simply means the equality of variance of normally distributed data of two or more samples. I'll take, for example, if this graph represents the normal distributions of 3 different samples, you could see that although samples 2 and 3 have similar mean values of 100, their standard deviation and, of course, by implication, their variances are different. On the other hand, samples 1 and 2, though with different means, have the same standard deviation and by implication, the same variances. And therefore, we could say sample 1 and 2 are homoscedastic, meaning they have equal variances. But samples 2 and 3 are heteroscedastic, they don't have equal variances. So these are some of the things that we need to check when we are comparing means of samples, which I'm still going to talk about in a moment. So one other thing that you need to keep in mind is that, just like normality, it's always better to conduct a statistical test, to compare, to really show whether a sample, data set have equality of variances, not just only by visualization like this. And you should also note that the number of your sample will determine, the kind of test that you could do to confirm whether your your samples have equal variances. So if you have 2 samples, for example, you'll be talking about Hef test. But if you have 3 or more samples, you have a plethora of options like Levin and other tests that you could pick from. So again, you need to really go back into into the paper to try and dig out some more information about which one is you need to choose when you are applying some of these things. So again, I just want to refer us to go back to the paper. We've not got enough time to dwell much into the details of some of these tests. So now, how do we select the right statistical method to compare the means of our samples? Should we use a parametric or a non-parametric test? As a matter of fact, means comparison is one of the most common statistical procedures we apply as food scientists and technologists. For example, we often need to compare a control sample to 1 or more newly formulated samples. So, and the answer to this question, which I've posed here, is simple. It all depends on the outcome of a few statistical steps which we have to take. And by that, I mean, when you have 2 samples or 3 samples, the first thing you need to do is to check for normality, as I've discussed earlier. And if your data is normally distributed, then you need to look at the variances of the samples. Do they have equal variances? Like I've just shown, if they have equal variances, then the option is to select a parametric test. For example, if you are using 2 samples, then a student t-test, whether paired or independent t-test, will be an option to compare the means of your samples. On the other hand, if it's 3 or more samples, you'll be talking about ANOVA. But what I've noticed is that many of our researchers, anything they are comparing, they just go straight to ANOVA. ANOVA is not always the solution or the statistical procedure we should follow. We should learn to follow these standard steps to really know whether we need to use parametric tests like ANOVA or t-test, or their non-parametric counterpart like Mann-Whitney or the wedge test. So again, we don't really have much time, but one thing I also add here is that non-parametric statistical tests obviously have the advantage of not requiring normality and equality of variance, but arguably they are not as powerful as the parametric test in detecting differences between or among samples or treatments. So, and there are other differences or some other information that the authors have cited, which we can find on on page 142 to 145 of the paper. So I would quickly like to move on to bivariate correlation analysis, which is particularly useful when one is interested in exploring if there is a possible linear relationship between two variables, such as the example here in which the authors, they were looking at the possibility of a linear relationship between oxidative deterioration of unsaturated lipid, that's linoleic acid, and the N-hexanyl compound, which is the off flavors that brown rice produce during storage. So they were looking at the correlation, the linear correlation between these two variables. And obviously this graph shows that there is a strong positive correlation between the two variables. But one thing we need to note is that when you are conducting a correlation analysis, you could, of course, see a positive correlation. You could see a negative correlation. You could even see, near zero correlation. But a zero correlation does not, necessarily mean that there is no correlation between the variables. It could mean that the relationship is non-linear, because what a bivariate correlation like this does is just to explore if there is a linear relationship. So when you have zero correlation in some, in your analysis, sometimes it doesn't mean that there is no relationship at all. It could just be that the relationship is non-linear. So some other things that we need to pay attention to when using correlation is that, number one, when we have when we have to use a correlation, we need to check our sample size. We need to check the sample size of the two data sets we are trying to correlate. Obviously, the authors here, recommend at least 8, but it should be noted that some other authors have recommended a minimum of 6. So if you have, 6 as the sample size of the data set, you're good to go. Number 2 thing is you need to check for normality of the data sets. So any of the tests that we mentioned earlier can be used. And if the data is normally distributed, then go ahead and use a Pearson correlation. Otherwise, the option is to use a Spearman correlation. And Spearman correlation is actually flexible, whether the data is normally distributed or whether one of the data is normally and the other is not, normally distributed. Spearman correlation can do the job. So the other thing which we have to note is that the coefficient of correlation which we obtain from either Pearson or Spearman correlation analysis are not enough to claim that a relationship exists between two variables. And this is because this coefficient could be easily influenced by the sample size. So the right thing to do after obtaining the coefficient of correlation is to test the significance of the correlation by calculating the p-value of the correlation coefficient. So this is done, in the same way the t-test is, carried out. And of course, many of the software that we use for statistical analysis have inbuilt, package for all of these things. So one more thing I need to emphasize is that correlation doesn't always mean causation. This, I know most of us would have had this, just like, in this graph where we have a strong correlation between ice cream sales and shark attacks. Does it mean that ice cream sales is caused by shark attacks, or vice versa? No. So it doesn't always mean, although in some situation it could be, but it doesn't always mean. So we need to watch out for that as well. So moving on to the last concept discussed by the author, which is regression analysis. One quick thing to note is that regression is different from correlation. Many of our researchers, they mix this up. Regression is different from correlation. Although to build a linear regression model, you need an evidence of a linear correlation between the two variables. And once two variables are linearly correlated, a regression model is just a way of representing that relationship mathematically, so that one of the variables can be predicted based on the knowledge of the other. And thankfully, the authors have highlighted some interesting information which we need to pay attention to when using regression analysis in this paper. You can find that information. I would implore us to go on and check them out, on the pages highlighted on the screen. On a final note, I just have a few comments. To me, the authors did a good job. They have been able to demystify, some of the statistical procedures many people struggle with. And I would gladly recommend this paper to both beginners and experts in the field. Although I feel like, the authors could have improved the readability of this paper by being, concise in their writing. And, for future studies, I would like to see more studies that would, also demystify some more sophisticated multivariate statistics, such as principal component analysis, cluster analysis, factor analysis, neural networks, etc. And of course, finally, I would also like to see few studies on how the choice of statistical software affects the outcome of statistical analysis that we do in food science and technology research. So on this note, I want to say thank you to everyone, and that's all I have.